In this lesson, we're going to prove identities that use the trig functions like sine and cosine. A good place to start is to go over what we already know about these functions. So just a few things, maybe just to list out the basic functions that we have. Let's see, there is sine of theta, and then there is cosine of theta. And after this, we can define tangent. So here it's worth going over, well, what is tangent of theta? If you know sine and cosine, tangent is defined from these two things. It is the ratio of sine to cosine. So basically, you divide those two things, and that's what we call tangent. There were three other trig functions. There was cosecant of theta, there was secant of theta, and then we also had cotangent of theta. So what are those? Well, they have definitions based off of sine and cosine as well. Cosecant is the reciprocal of sine. So if you see cosecant, that really means 1 over sine of theta. Likewise, secant of theta, that is the reciprocal of cosine. And you can define cotangent as the reciprocal of tangent, but I'll just take this fraction and flip it and write that out as, well, that is cosine of theta over sine of theta. So even though we have these 6 trig functions, 4 of them are defined off of these two to start with. Okay, so one other thing that I think is worth mentioning is the following identity. Sine squared of an angle plus cosine squared of an angle, which I'll call theta, it's always equal to 1. This is a very important identity, and it will probably show up in a lot of the problems that we're going to work on. So just as a quick reminder, where does this thing come from? Like, what is this? Well, sine and cosine themselves are defined off of the unit circle. So here's a circle of radius 1. And the equation that defines this circle is y squared plus x squared is equal to 1. So like if you put this into Desmos and graph it, it'll give you this circle. Actually, that's how I got this image here. Well, what's sine and cosine? If you draw an angle with the positive x-axis, and let's say I call this angle theta, you get a point on the unit circle. It has an x-coordinate and a y-coordinate, so you can write it as something comma something. Well, the x-coordinate is what we call cosine of theta, and the y-coordinate is what we call sine of theta, and that is an x and a y. If we take the x's and y's in this equation and replace the y with sine and the x with cosine, you'll get sine squared plus cosine squared is equal to 1, which is this identity here. So just kind of a quick reminder of what we're going to need in this lesson. Sine and cosine are defined off of the unit circle, and they yield this identity. The other 4 trig functions are defined from sine and cosine. So on the previous slide, we went over really quickly why sine squared of an angle plus cosine squared of that same angle is always equal to 1. We call this a Pythagorean identity, and there are 2 others. Tangent squared of an angle plus 1 is equal to secant squared of an angle, and 1 plus cotangent squared of an angle is equal to cosecant squared of an angle. Why are these 2 things true? We can actually use this identity to arrive at these 2 identities, and I'd like to go over that now. So how can we prove this from this? So below here, I'm going to just copy down that identity of sine squared plus cosine squared of the angle theta is equal to 1. How can we transform this into this? Well, here I see that we have a tangent squared, and here I have a sine squared. One way that you could make sine squared become tangent if this had a cosine in the denominator. So what I'm going to do is divide both sides of this equation by cosine squared. That means I can divide each individual term by cosine squared. Now, if I do this, I did the same thing to the left and the right side of my equation because I divided everything by cosine squared. Sine over cosine is what we call tangent, and here we have 2 in the top and 2 in the bottom. So from this step here, not only do you have tangent of theta because you have sine over cosine, but you actually have tangent squared because you have two copies of them. Okay, so this next piece here, we have cosine squared over cosine squared. When you divide the same thing in the top and the bottom like this, it's going to equal 1. So that's where this 1 comes from. And on the other side of my equation, I have 1 over cosine squared of theta. Well, from the previous slide, I reminded us that, well, secant is the reciprocal of cosine. Well, if we have two copies of cosine in the denominator, that means we also have secant squared, like this. Secant is 1 over cosine, so secant squared is 1 over cosine squared. And just in this one step, we got from this identity here to this one. So how about proving this identity? How can I demonstrate that this is true, again, from starting with this identity? So let's look at that again. I'm going to copy down sine squared of theta plus cosine squared of theta is equal to 1. All right, this time, a couple ways to think about it. I see I have a 1 here, and here I have a sine squared. If I want to change the sine squared into a 1, I could divide by sine squared. Now, if I do that to this term, I have to do it to every term, to both sides of my equation. So what I'm going to do is divide both sides by sine squared of theta. So I did the same thing to both sides. If I look at this fraction here, sine squared over sine squared is equal to 1, so I'll just put down a 1. Okay, I'm going to add on. Now here I have cosine over sine, and that is the definition of cotangent. And because I have two of them in both the numerator and the denominator, I don't just have cotangent, but I have cotangent squared of theta. So that looks like the left side. On the right side, I have 1 over sine squared. Cosecant, as a definition, is 1 over sine. So if I have 1 over sine squared, that means I have cosecant squared on the right. And that proves this identity here. So these identities are good to know, and they might show up in some of the problems that we work with. In example 2, I want to prove several identities, and I want to start with this one here. Sine of theta times cotangent of theta is equal to cosine of theta. Now, this one's going to be relatively simple, but it will go over the general procedure that we'll use when proving identities. The idea is choose one of the sides, like maybe the left side. Work with only this side, but try to simplify it to make it look like the other side of the identity. Really what we're saying here is, are these two things actually true? And we have to prove it. So when I look at the two sides, you have to pick one of the sides. It's better to choose the side that actually gives you something to work with, perhaps the side that is more complicated. I look at cosine of theta and nothing's jumping out at me. But if you look at the left side of our identity, well, I'm seeing there's two things being multiplied together. Maybe that gives me a little bit more to work with. So my strategy is going to be, let's work with the left side of this equation. So what can we do? All right, well, I have sine of theta, and then I get to cotangent. Well, I know cotangent has a definition, so I'm just going to replace cotangent with how it is defined. The definition of cotangent is, let's see, I believe that was cosine of theta divided by sine of theta. And still we're asking, is this actually equal to cosine of theta? There isn't a lot of extra work to do here, but I can see what I'll do in my next step. Okay, well, maybe I'll write this as a fraction. I can say that this is really, it's sine of theta over 1 times cosine of theta over sine of theta. Is that in fact equal to cosine of theta? And it looks like the answer is yes. Once you replace cotangent with its definition, and it's sitting here, I can cancel these factors of sine. So I can say, well, this sine cancels with this one, and we have 1s that are left over. So in fact, the left side of my equation, it's 1 times cosine of theta over 1 times 1. That's just the same thing as saying cosine of theta. And on the right side of my equation, I also have cosine of theta. Clearly, these two things are equal, And this is what it means to prove an identity. This one was relatively simple, but it really goes over a good strategy. Choose a side to work with, probably choose the more complicated side, refer to some definitions, maybe some other identities that you know, simplify, and then make sure the left and right side are actually the same. So again, I want to try to prove that this identity is true. So here we have a brand new identity. Does the left side actually equal the right side? There's more than one way to prove these. I'm just going to pick what jumps out at me. And between the left and the right side, it looks like the left side is more complicated. There's more than I can work with. So I'm not going to do anything to the secant squared, but I'm going to try to make this side look like this side. Let's see. Well, I have this 1 plus, so I can't do anything with the 1. I'll just put, got 1 plus. And I see that we have secant, tangent, and sine. Maybe I'll replace secant and tangent with their definitions in terms of sine and cosine. So for example, secant is 1 over cosine of theta. And tangent is sine of theta over cosine of theta. And then for the sine of theta, well, I won't do anything to that. I'm just going to leave it alone. And the question is, well, will this simplify to give me secant squared of theta? Okay, well, I'm looking at this portion here, and I'm going to try to combine things or cancel things. Nothing cancels this time, but if I look at the numerator, I have 3 fractions, and I can simply multiply across 1 times sine is sine squared. So just to look at the left side, I have 1 plus, and I have this fraction. And 1 times sine is what we call sine squared, and it's of the angle theta. In the denominator, I have cosine times 1. Likewise, that's going to be cosine squared of theta. And that is, is that equal to secant squared of theta? So I replaced things with some definitions. I started maybe combining some things together. And I've done nothing to this side. I've left this completely alone. And here we are. Is this thing a true statement? Well, I think I can simplify this part on the left side a little bit more. I know sine over cosine is what we call tangent, and it's squared, so I know the left side is actually 1 plus tangent squared of theta. And, is this equal to secant squared of theta? And the answer to this is yes. In example 1, we actually prove that this identity is true. We show that 1 plus tangent squared of theta can be replaced with secant squared of theta. That is clearly equal to the right side of this equation. So the left side does in fact equal the right. Since all of these steps are reversible, if this is true, then this original one is true as well. All right, let's see if we can prove tangent of theta times sine of theta is equal to secant of theta minus cosine of theta. There's, there might be more than one way to do this. Like you could make the right side look like the left, perhaps the left look like the right. I'm not really sure, just looking at this one. I think this time I'm going to leave the left side alone, so I won't do anything to this, but I'm going to start working with the right side of the equation. Can I make this thing look like this? Let's see. So I'm going to just copy down tangent of theta times sine of theta. And, is this equal to the right side? Okay, so I've secant of theta minus cosine of theta. I'm going to leave the cosine alone, but I know secant has a definition. Its definition is 1 over cosine of theta. So these two lines are equivalent to each other. All right, what next? Again, I'm not going to do a thing to this side of my identity. I'm going to work with this side here. Now, I see I have 2 fractions. Specifically, if I write this cosine of theta as cosine of theta over 1. A way to move forward in this problem is, well, why don't we actually subtract these 2 fractions by getting a common denominator and then subtracting the numerators? So that's what I'm going to do to move forward. I see 2 fractions. I'm thinking, let's subtract them. My least common denominator here is going to be cosine of theta. And what that means is I'm not going to do anything to this denominator, but this one, I have to multiply in cosine of theta. But that means I have to do the same thing to the numerator as well. So moving forward, we have tangent of theta times sine of theta is equal to, hopefully it's equal to, I have my common denominator of cosine of theta. This numerator is a 1, so I'll just copy down a 1. And then we're going to subtract, well, cosine times cosine is what we call cosine squared. So minus cosine squared of theta. All right, great. So now what? I know at this point I'm just going to make a note. We proved earlier, or we referred to the fact that sine squared of theta plus cosine squared of theta is always equal to 1. I just referenced this rule that we had, this identity we already know. Now, I don't see sine squared plus cosine squared here, but here's what I do see. If I subtract cosine squared to the other side of this identity, I know that sine squared of theta is equivalent to 1 minus cosine squared of theta. So this thing right here, this 1 minus cosine squared, is actually equivalent to sine squared. So I'm going to replace this with this. Let's try it out. Again, I'm not doing anything to the left. But on the right, okay, 1 minus cosine squared is equivalent to sine squared of theta, and that's being divided by cosine of theta. I feel like we're getting pretty close here. Now, I can look to this side as guidance, like where I'm trying to go. I know I want a sine by itself, but I also want a tangent. And I know tangent is defined as sine over cosine. If you look at this numerator, you can actually break it up into sine times sine. So I'm going to do that. Again, leaving the left side alone. Okay, this is really sine of theta times sine of theta, and that's all over cosine of theta, like this. In fact, I'm going to kind of cheat a little bit here and say, well, these things are being multiplied together. I could really just write this cosine in the denominator of this sine. So I'm going to get rid of this division part and just think of it as like two separate pieces. So this line here is equivalent to this one. And if you wanted to, you could say, well, I know it's really a fraction here. This line and this line are certainly equivalent. Sine squared is sine times sine. We can think of this as multiplying two separate fractions together. I wrote it this way because, well, here I have sine over cosine. That's tangent. So copy down the left, leave the left alone. And then I'm multiplying by sine of theta over 1, which is just sine of theta. And there it is. Working with just the right side and using an identity, I was able to simplify down to this thing here. So this is enough to prove this original identity. All right, what about this one? This looks pretty complicated, this identity here. Let's see. I think working with the left side makes more sense than the right. I see I have two fractions. I already am thinking like, okay, I have a place to go. I could try to add these two fractions together by getting a least common denominator. Whereas on this side, I don't think I have enough to work with to make it look like the left side. So that's a good starting point. I'm deciding to work with the left. Now, we need a least common denominator if we want to add those two fractions together. And that least common denominator, it's kind of complicated, but it's going to be the product of the two separate denominators. So what I'm going to do is, I'm asking if these two things are actually in fact true. What I'm going to do is multiply this fraction by sine over sine, and I'm going to multiply this fraction by 1 plus cosine over 1 plus cosine. That will be enough to get me my least common denominator. So that is, I'm multiplying sine of theta over sine of theta to the fraction sine of theta over 1 plus cosine theta. And then we're adding that to, and in the other fraction, I'm multiplying the top and bottom by 1 plus cosine theta over 1 plus cosine theta to the fraction 1 plus cosine theta over sine of theta. And again, is this ultimately going to equal 2 cosecant of theta? Hopefully it does. We'll see. Well, the good news is we do actually have a least common denominator. We have the product of those two things times the product of those two things. On the left, I'm just going to write one fraction. And the denominator of that fraction, I'll write it as it's sine of theta times 1 plus cosine theta. I know on the other side, I'm asking, does it equal 2 times cosecant theta? Now, in my numerator, okay, here I have sine times sine. I'm going to write that as sine squared of theta plus, now here, I'm multiplying this numerator by this numerator. And really, that means I gotta be careful. I gotta distribute here. So I'm just gonna put some parentheses. And why don't we actually do the multiplication from this step down to this step? And by that I mean, well, you're gonna multiply this 1 to this 1. So that gives you a 1. I'm going to multiply this 1 to the cosine of theta, so get a plus cosine theta. Hopefully I'll have enough room. We now have to do the same thing. We have to multiply in the cosine of theta. So cosine gets multiplied to 1, so we get another cosine. And then we have to multiply the cosine to this cosine, and it gives me a cosine squared. Oof, just got enough room there. Okay. Well, there's some simplifying that we can do. Let's combine some like terms and go from there. Okay, so on the left, again, we have this denominator of sine theta times 1 plus cosine theta. And in the numerator, I have sine squared of theta. I have 1. I have 2 cosine thetas, and then a cosine squared of theta, like that. Is that equal to 2 cosecant of theta? Oh, well, here I see something. I see that I have sine squared and cosine squared. These two can be combined to give you an additional 1 in the numerator. So here I'm referencing the fact that, well, I know sine squared of theta plus cosine squared of theta it's really equal to 1. So this here and this here, I'm just going to replace with 1. I think this is definitely going to be a longer question, but I'm going to write 1 plus 2 cosine theta all over sine theta times 1 plus cosine theta, and ask, is that actually equal to 2 cosecant of theta? So I was able to replace this and this with that 1. I'll continue this on the next slide, and I'm going to add these ones together and put a 2. Let's see what we get. So here's where we left off. I'm going to add these two together and just write 2. So on the left, this is really 2 plus 2 cosine theta divided by sine of theta times 1 plus cosine theta. Is that equal to 2 cosecant of theta? I see I can factor a 2 out from these terms, and I'll be left with 1 plus cosine of theta, which is great. I think that means we're going to be able to cancel a factor. So let's see, I'm going to write the left side as, well, that's really 2 times 1 plus cosine of theta. That's all divided by sine of theta times 1 plus cosine of theta. Is that actually equal to 2 cosecant of theta? And great, we can cancel this. This whole thing cancels with this. And we are left with 2 over sine of theta. Hey, is that actually equal to 2 cosecant of theta? And the answer is yes. The reciprocal of sine is cosecant. So 1 over sine is equivalent to saying cosecant of theta. We showed that the left and the right side are actually equal. That means each previous line is equal as well, and so is the original identity. In this identity here, I think the left side is better to work with just because there's more options of what to do. There is, probably more than one way to do this, But what I'm going to do is replace secant, cotangent, and tangent with their definitions with sines and cosines. We're going to have fractions within fractions, but it gives us a place to go. On the left, this is going to be equal to something sine of theta, whatever. In the numerator, secant of theta, by definition, is 1 over cosine of theta. In the denominator, cotangent, well, that's cosine of theta over sine of theta. And to that, we're going to add, well, tangent is sine of theta over cosine of theta. Where do we go from here? I think a good next move is going to be, I don't like fractions within a fraction. Can we somehow get rid of the denominators cosine, sine, and this cosine? The trick is to multiply each fraction by the least common denominator between cosine and sine. So that least common denominator is actually sine times cosine. I'm going to multiply each of these 3 fractions by sine over cosine. It'll cancel the fractions within fractions. I think I can fit that all here. Let's see. In the top, it's going to be multiply sine theta cosine theta over 1. We're going to multiply that here, sine theta cosine theta over 1. And we're going to multiply that here as well, sine theta cosine theta over 1. We're multiplying the top and bottom by sine of theta over cosine of theta. This will not alter what the fraction is equal to. But by doing this, okay, I can cancel this cosine with that cosine. In just the numerator, the denominator is only 1. We don't even really need to write that anymore. We're actually just left with sine of theta. Perfect. In the denominator, let's see, I can cancel sine with sine, and we're just left with that cosine times cosine. And here, this cosine can cancel with that cosine, and we're getting there. We're making this look a little bit nicer. On the left, in just the numerator, there's only sine that is left over. There's no longer a fraction, but we have sine. In the denominator, we have cosine times cosine, so I'll put that's cosine squared of theta, plus, okay, I have sine times sine, that's sine squared of theta, and hopefully, maybe, that's actually equal to sine of theta when all is said and done. And I know the answer at this point. This is going to work out. I know that sine squared of theta plus cosine squared of theta is equal to 1. That means this whole thing here, it's written backwards, but it still is equal to 1. This is sine of theta over 1. Is that equal to sine of theta? I mean, I don't need to write another step. That is definitely true. If this is true, so is each previous line, including this original identity.